Hello, physics students. This is Mr. Bornheimer. Today, I'm going to talk to you a little bit about pendulums and whatnot. If you go to the B Classroom website and you click on the homework link off on the right-hand side, you'll see that I've posted my lesson plans for the next 2 weeks. And it's right here in Physics 12.3 to 12.21. If you go down to the bottom, you can hit Read More, and then it gives you the full lineup. And I want to kind of go over this with you real quick to just emphasize a few things today. First of all, yesterday we talked about simple harmonic motion and restoring forces, and you can see that that's kind of what we did here. We reviewed the homework. If you have any additional questions, please, 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 if you see here's the student question forum, post a question there, and I will do my best to answer it. Every time you post a question or respond to another student's question, you do get extra credit. Okay? Today, I'm going to talk to you about harmonic oscillators and diagrams, and I'm going to demonstrate to you a pendulum. Now, obviously, because this is a recording, you're going to have to do a little bit of your own thinking about this. You do have a pendulum lab tomorrow, as you will see, and I will not be here tomorrow as well. So what I'm going to do is I'm going to talk through pendulums today. I'm going to try to give you at least an online demonstration of a pendulum, do my best. I showed you kind of a video. If you wanted to look it up yourself, you could watch, just search pendulum waves on YouTube. We kind of watched that yesterday. And the lab will be passed out to you today in preparation for tomorrow. Tomorrow there'll be no video, okay? So just be aware of that. Now, so today I'm going to talk to you about harmonic oscillators, diagrams, pendulums. I'm going to go over the lab, okay? Tomorrow you'll do the pendulum lab, and you will have homework on top of finishing the lab. Okay, Thursday, you will have a homework quest, and that will include pretty much everything from page 136, so tomorrow night's homework, to page 151 and 154. Okay, and like I said, if you have questions, post it in the student question forum, and then that way I can answer them or some other student can answer them for you and get extra credit. All right, now on Thursday, we're going to go over the homework quest. We're going to go over some practice problems. Okay, we're going to review, you will receive a review sheet of chapter 5 and 6, basically looking at those equations for displacement, final velocity, force vectors, things like that. Friday is a little bit easier. We'll have a movie Friday, and Alex, if you remember, that is your day, so make sure you bring a movie. Please email me, Alex, what you plan on doing, and make sure you have a handout with fill in the blanks ready, so as you explain your topic, everyone else can follow along. Okay? And then we will end Friday with this problem right here. And I would advise you to take a look at that ahead of time. We may not finish it, so we may finish it on Monday, but Monday starts the beginning of our tough unit, projectile motion. I will do two demonstrations, one called a motion cart and one the sphere drop apparatus. All right, this is based on pages 155 to 161. And then I will talk through two different scenarios. Tuesday and Wednesday are one problem. Thursday and Friday are another problem. You're going to be taking home a test the weekend before finals. Now, it's only part one of a test. It's just a problem similar to what we did Tuesday through Friday. When you come back on Monday, you'll finish part two, which will be equilibrium problems like equilibrants and an object on a slope. Tuesday will be a self-guided study. So you bring the questions, and I will do my best to answer them for the final exam. And then you have a couple of days where you can ask me questions in between, and Friday is your final exam. So I just wanted to give you a quick rundown in these 4 or 5 minutes at the beginning of class just to show you kind of what the outlook is. If this was hard to read, the text was too small, whatever, you can find this on my website at the Mr. B's Classroom Homework and News page, which is under the Homework tab, a homework link in Student Resources on my website. Okay, so you can find that here. Okay, so I just wanted to cover that with you. Next thing I want to talk about is the Pendulum Lab. Okay, and I'm going to bring that up right here. The Pendulum Lab is, and I'm going to talk through this. Pendulums basically are a mass on a string that swings back and forth. You're probably more familiar with the pendulum in a grandfather clock. Okay, that's a type of pendulum. There are other types of pendulums called fulcrum pendulums, which actually move with the rotation of the Earth. And there are a couple of famous ones around the world. You should check it out on YouTube. They're kind of cool. They're actually really kind of cool. All right, the purpose of this lab is to determine the factors that affect the time it takes for a pendulum to make one full oscillation. A full oscillation would be going from the left side to the right side and back to the starting position. Okay? The rest position of a pendulum is where it hangs when it's not moving, and that would be this center pendulum right here. And I'll zoom in a little bit here for you. If here's a pendulum that's swinging back and forth, this center one, if it was still, we would call that the rest position. So here's the start position, the rest position, and what happens is the pendulum will swing through, slow down, stop, and come back. And we call that one full oscillation. Okay? Make sure you're taking note of this. All right, now you're going to be varying three things. You're going to be varying the weight, or actually I probably should say the mass, the height of release, okay, above the rest position, and the length of the string. All right, so these are the three variables that you're going to try to use and view and observe and change. Now remember, anytime you're changing one variable, the other two have to be constant. Okay, so make sure that you're not changing all three at the same time, and it's pretty hard to do that in this lab. These are all the things you're going to need. I would advise you to take a look at the back of the room right now. You'll notice on the center table, there's already a pendulum set up. You'll notice that the pendulum is attached to a mass, and there's a string, and that the ring stand, which you used in chemistry, is C-clamped to the table. Not very tightly. You don't want to ruin them or bend them, but it's attached to the table. So what you have going on here is you're gonna use these pendulums, and you're gonna vary different things. You're gonna vary how high you lift the pendulum from its rest position in the vertical direction. You're gonna vary the amount of mass on the end of the string, and you're going to vary the length of the string. There's a variety of different ways you can do this, and one of the things you're going to probably struggle with the most is trying to figure out how to get the string different lengths. Okay, I've provided some tape if you need to tape the string, but just make sure that when everything is taken apart and properly dismantled before you are done with when you are done with the lab. Now, one person needs to be a timer, one person actually needs to be the experimenter, and one person needs to record. If you only have two people in a group, make the timer and the reader and recorder are probably the same person. The experimenter is going to be the person that pulls the pendulum back, lets go, and counts the number of times it goes back and forth. So here's the initial setup. You're going to fasten the ring stand to your lab table with a C-clamp so that it's motionless. Make sure that when you swing your pendulum, it does not hit the stand or the table. Practice with your team to be sure that you understand the timing procedure, timing it for 5 full oscillations. I find it useful if the experimenter holds out an index finger at the point of maximum swing and counts out the number of swings as the pendulum returns to the finger. Okay, so you're going to play around. At first, you're just going to play around a little bit, get a hang for how the pendulum works. In the first experiment, you're going to change the mass. Okay, and I would advise you to read through this. Ultimately, you start with a small mass, and you ultimately work up to a larger mass. The length of the string is not going to change. The height from which you release the mass cannot change. Okay? Now, 2, you're going to increase the height. So you're going to start with a string no greater than 50 centimeters, and you are going to move the mass vertical so that it's raised a vertical distance of 10 centimeters. Vertical, not to the side, vertical. And it's going to be tricky to use a meter stick and measure that distance, but I am confident you guys can do that. Then you are going to raise it to 20 centimeters, then raise it 30 centimeters. And you might have to eyeball it, but you need to be close to those. Okay, experiment 3. You're going to vary the length of the string. Okay, now, in each hypothesis, you need to circle what do you think will happen to the period. And remember, the period is the time it takes for the pendulum to complete one full oscillation. That is one full back and forth motion. Okay? So you're going to tie the 100-gram mass to the end of a string no more than 50 centimeters in length, and you're just going to read through the instructions. Now, because you're getting this the day before the lab, please read through the instructions when I am done with this video carefully. If you have any questions, note them and email me or post them on the student question forum so that I can answer them immediately. Because if you don't post them or you don't ask them, you won't necessarily know what to do. Okay? Now, you'll given 3 data tables. Okay? You have 3 trials per setup. And so like here where we're changing mass, you'll write the mass here of the first pendulum, what we call bob. It's the hanging mass. You'll swing it once. You'll write down the total time for 5 swings. You'll do the same here and here. You'll write the average, and then you'll divide the average, okay, by 5. Okay, so you're going to go ahead and figure these out. Actually, hang on one second. Average time for 5 swings at each mass. Average time for 1 swing at each mass. Yep, you're going to divide line 4 by line 5, or by 5, the number 5, and then they'll put that number here. And that's the time, the average time it takes for the pendulum to complete 1 full oscillation. You're going to do that for each mass, record all the data. Then you're going to do it for each height, record the data. Then you're going to do it for each string length and record your data. The last thing you need to do is you need to fill out the post-lab questions. And I will talk about when these are due upon my return. The odds are that this lab probably won't be due until after Christmas. It's not a big assignment. It is some points, okay, but it's not really that big of an assignment. Okay, it's not going to be due the day you get back from break, but it will be due when you get back from break. It's not a major project, but you are going to probably be given a day in class to work on it. When you get back, or at least the graphing portion. So when you come back from break, you should have the other things done, and then we'll work on the graphing, maybe part 3 and 4 when we get back. We'll give you a day in the computer lab where you can create the graphs. Okay, so that's the lab, and you're going to have a little bit of time at the end of class today to maybe set up your apparatus and get ready for the lab, so that you are good to go tomorrow when you do this lab. All right, I'm going to start today talking a little bit about some diagrams online, and kind of talking about oscillators. Yesterday we talked about simple harmonic motion. Simple harmonic motion, by its very definition, is what happens when an object oscillates at regular intervals back and forth. Now, true simple harmonic motion, there is no resistance, no air resistance, no friction or anything, and the oscillator would go on forever. Any kind of resistance in an oscillator, like a pendulum or a spring, is called damping. Please write that down. It's called damping. Without any sort of damping, without any sort of resistance, the spring, the pendulum, would swing forever. Okay? Now, in the online, in Unit 3, there are a couple of animations and shockwave files that you can use to kind of look at some of these concepts. I'm going to start with the animation, and it's a GIF image. And you'll notice that if you click on it, it kind of shows the object going up and down, oscillating back and forth at regular intervals. You'll notice that this is periodic, meaning that it does so in the same fashion each time, kind of like the pendulum, which we will explain more in depth in just a minute. All right, so there's a simple harmonic oscillator. You can see that in that folder. There's also, okay, shockwave files, and these are kind of cool. Okay, I'm going to go ahead and click on this. You have to download these. But to open these shockwave files, you use the internet. So I'm just going to use Firefox. And it actually opens up an animation here. And you'll notice that as the mass goes above the equilibrium position, okay, it's being forced back in the other direction by gravity. And then as it goes below the equilibrium position, it's being forced up by the spring, and it goes back and forth in its simple harmonic motion. The next diagram, the next shockwave file is actually considerably more interesting because it shows, it varies one of the variables, and that's this one. Notice that if I put a small weight, look what happens to the speed of the oscillations. Okay, now this is with springs, mind you. If I go to a medium weight, it slows down a little bit. And the reason being is the greater the mass, the greater the object has to resist a change in motion. If you remember or recall, that is Newton's first law, the law of inertia. The greater the mass, the greater the resistance to a change in motion. If we go with a large weight, it's even slower yet. You can actually download these, click the buttons, see the change from small to large, okay, and things like that. The last one I want to show you, and I kind of hinted at this yesterday, was what we call the sine wave production of a harmonic oscillator. And when I was talking about the spring going up and down, if you thought of it as a particle, okay, going up and down on a wave, it would actually produce a sine wave or a cosine wave. If you notice that this disk is spinning, okay, now if we were to advance this point and look at just its vertical motion by doing something like this, so we draw on this line and we're looking at just the vertical motion, we can see that the displacement is from here to here. Okay. Now if we look at just the 2D effects of this, we can see that it creates a sine wave. Now, if this wasn't spinning all the way around, if it was a harmonic oscillator just going up and down, look at this, look at the bar. It just goes up and down. Up, down, up, down. Just like the spring yesterday was going up, down. Just like the pendulum's vertical motion will just go up and down. It's actually what we call a sinusoidal wave generator. Okay? Just something kind of throw out there. We're not actually going to do any math with this. It's just a concept that you should be familiar with if you go on and take any sort of physics class at the college level. Okay? All right. So here we go. I'm going to spend just a couple of minutes kind of going through what a pendulum is and and things like that, and different variations on the spring mass, and then we will you will be able to do the lab for tomorrow. I want to start with the spring and the mass again today, and we're going to start with a spring, and it's going to be attached to a mass. Oh, we can make that the mass. That's fine. I'm going to move that though. And I'm going to kind of fill it in, make it green. Okay. Now, I'm going to draw several variations on this. So I'm actually going to go ahead and copy this or clone it. So it's over here. And then I'm going to clone it again. And you're going to see why I'm doing this here in just a second. I'm going to move this over. I'm going to move this over. I'm going to move this over. I'm going to clone this. Okay. Now, what I'm going to do is I'm going to say that this is at the, and I'm going to go ahead and choose a red color. This is at the rest position. And let's say that we give an initial displacement to our object by pulling it downward. Okay, so I'm going to go ahead and I'm going to stretch. Having a hard time here. Okay, I'm going to stretch it down. Now, we also are going to see, and then there's this one, and then I'm going to show you kind of what happens when it comes back the other way. It's actually right about there. Okay, if you have a spring at rest, it looks like this, and I showed you that yesterday. Gravity is coming down, gravity is affecting this force, and we see that gravity is pulling down. We call that the force of gravity. But the tension in the spring is providing an equal and opposite force in the upward direction. We call that force tension. Now, when I pull down on this spring, the force of gravity doesn't change. Okay, but the tensional force gets a lot stronger. Okay, and you can kind of see that there. The tensional force gets a lot stronger. And if I can move that over to the side, I can show you that it actually is greater than the force of gravity in the downward direction. So when I release the mass, the net force is going to be in the upward direction, which means that the object, because there is a net force in the upward direction, that net force is going to be here, and we're going to call that F net. As that force is accelerating, the object is accelerating upwards. Now, because it has acceleration, it's going to go through the rest position, but because of momentum, which we haven't talked about yet, which is a force that allows an object to carry on its motion, because the object was accelerating, okay, it's going to go through the rest position and upwards. Now, as it goes through the rest position, the tensional force and the force of gravity are the same. But because now it has an acceleration in that direction, the object is going to accelerate in that direction. And if you think about it in the terms of inertia, okay, an object in motion will stay in motion unless acted upon by an outside force. The object, when it goes through the rest position, will be accelerating, but at a moment it goes through the rest, because the forces are equal and opposite, it will be zero. But the inertia of the object will carry it through so that it will then accelerate up and above and beyond. And that is why we have this object up here. Now, as it approaches up here, what happens is that the force tension gets really small. Okay, the force of tension actually almost becomes non-existent. It gets really small, whereas the force of gravity is still relatively large. So now what we see happen is that the force of gravity now becomes the net force. And now there is a net force in the downward direction. And so the whole process repeats. It now then goes down through the rest position where the force of tension and force of gravity are equal. But because of inertia, it carries on through. It'll go back down, okay, where now the tension will increase greater than gravity, thus reversing the effects and accelerating it up. And without any sort of resistance, this would go back and forth forever. Okay, so we see that by pulling it down, we create an unbalanced force on the system. It compensates, but because of inertia, it overcompensates. It goes over to this final thing where it slows down. So it's equal and opposite to this, where the force of gravity is now greater than the force of tension. And then, again, it accelerates in the opposite direction, again overcompensates, and goes on and on and on. Okay, so this is what's happening inside the harmonic spring oscillator system. All right, and I wanted to review that from yesterday. Like I said, if you have any questions, please post them to the student forum, and I would love to answer them and help to clarify any ideas that may be confusing you. All right, on to pendulums. First of all, pendulums. Here they are. A pendulum is nothing more than a string attached to a mass. We call the mass Bob. If you're familiar with construction at all, there's an object that people will use to see if something is straight up and down. It's called a plumb bob. Okay, pendulums have all been around for a long time. The Egyptians used them when creating the pyramids to help align everything up so that it was perfectly aligned. They've been around for centuries. Okay. Now, what happens in a pendulum is very similar, and you can actually see this in your book. I posted on B Classroom what pages specifically. I don't quite remember. I think it's page 136. There's a great diagram of this. When the bob is here, okay, the forces acting on bob are the force of gravity and the force tension, which are equal and opposite. So the force of tension and the force of gravity. We call this the rest position, because the pendulum is at rest. Okay, now, going to the next page, when we move the pendulum by raising it a certain height, and this is going to become important for your lab tomorrow, we go ahead and do something like this, where we take Bob, okay, and we move it so it's somewhere out here. We're going to shift this string. Okay, now, if you recall, Bob was originally right here. What we've done by pulling it up, okay, we pulled up in this direction, is we've raised Bob from this displacement, which we call D initial, the initial displacement, to this displacement, which is D final. Okay, we've actually raised Bob a height. And that's what I'm talking about when you vary the height of the pendulum. That's what you're going to do in the lab. You're going to vary this distance from D initial, where the pendulum starts, to where it is. You're not going to worry about the distance in this direction. You're going to worry about just the distance upwards, why I call it the vertical distance. Okay, so we're going to be worrying about that. Okay, so there's the rest position. Now, what's happening on Bob at this position is very important. When we raise him up, gravity is still acting straight down, but now Bob is at an angle. Okay? The force of tension is acting in this direction, but the force of tension is acting at an angle to gravity, and thus the component vectors come into play. There is both a horizontal component and a vertical component. Now, the vertical component of this tensional force has to be equal and opposite to gravity. Now, gravity and this vertical component will cancel, but that leaves this component right here, which is the net force acting on the bob. And it drives the bob to try to move in this direction. But the bob can't move purely horizontal. It's attached to a spring. So it travels down through its rest position and up over here. Now, as it travels down through the rest position, this force here gets smaller until here, where the force of gravity and the force of tension are equal and opposite, 180 degrees. And then as Bob goes up, and I'm just going to use a dot to represent Bob, the force of gravity will continue to be the same. The force of tension will continue to be the same, but there will be an increasingly larger force acting horizontally. And it's this force that slows the bob down and then reverses the direction. Down here, there is no horizontal. And over here, the horizontal is little, and then it increases, and then to the point where it's bigger here. So we see that these arrows are really doing something like this. The net force on the object is really these arrows here. And it drives the bob inward towards its rest position. Just like on the spring, though, where as it goes through the rest position, it overcompensates, the pendulum does the same thing. It drives through the rest position, but because of inertia, it's carried on through. It has to be slowed down by the tensional force. Then it goes back through, overcompensates, and goes back and forth, back and forth, back and forth. Okay, so that is how the pendulum works. Okay, I would highly advise you, please, to read pages 134 to 136. Okay, there is an equation for the period of a pendulum, and we can kind of go over that here just a minute. This equation I would definitely keep in mind if I were you for the lab, because this equation gives you some insight into what you can expect to see with the lab. It's kind of one of those things where you look at it and you kind of figure out what might happen. All right, so here's the equation for what we call the period of a pendulum. Okay, so t equals 2 pi, okay, times the square root of the length over gravity, which is the acceleration due to gravity, which is 9.81 meters per second squared. Now, we use a positive 9.81 because the length is going to be positive, and you cannot have a negative under the radical. Okay. Now, please notice the period is the time it takes for the pendulum to go from here through the rest position to the other side, okay, and then back again. So every time, one period is where it goes from here to here and then back again. That is one period. A period, okay, t, is going to end up being in seconds, and here's why. Okay, you have the square root of length over gravity. Length is in meters. Gravity is in meters per second squared. Okay, now here's what happens. The meters cancel out. The second squared moves up, and you end up with the square root of second squared times 2 pi, which is unitless. The square root of second squared is just seconds. Okay, so this is the equation you will use. All right, and one of the great things about pendulums is this. Say you had a pendulum on the moon. Obviously, the pendulum is affected by gravity. So let's say you have a pendulum on the moon, and you know the length, okay, and you know how long it goes back and forth. You could calculate gravity because it's the only other variable in the equation. It is actually a foolproof way of calculating gravity on other planets or in a spaceship. You can actually calculate the gravity at a particular location by using a pendulum. It's actually a technique that is been considered because oftentimes a lot of our techniques, a lot of our equipment is based on Earth's gravity, but a pendulum is not. It is entirely dependent upon gravity as a variable, which makes it very useful if you wanted to calculate, say, the gravity on Jupiter. Okay? So this is the equation for a period of a pendulum. All right, now we're 30 minutes into class right now. You have about 15 minutes left. What I want you to do is I want you to set up the lab for tomorrow, read through the lab, write down any questions you have, okay? And then if you want to, you can start on your homework, which is on B Classroom. I'll pull that up here so you can see it real quick, okay? B Classroom homework. Tonight's, or what would be tomorrow night's homework, but you can get started if you like, would be page 136, practice problems 17, 18, and 19. Okay, page 136, practice problems 17, 18, and 19. If you have any questions, please let me know. You have a quest on Thursday. You have a lab tomorrow. Thank you for watching, guys. I hope that you have a wonderful, blessed day. Goodbye.